is not only kind of encapsulates what you're used to having, which is just like the elemental forms of it. So what it also includes within this now is a much broader list of polyatomic ions that are capable of acting as reducing agents or oxidizing agents. So it's the same list, but now it's much, much, much more broad in terms of what you're going to have. So it's still the exact same thing. It's still a reduction chart. So, but what you'll notice that, let's say for example, you have hydrogen peroxide up here, okay? So if you've ever had an infection and like a cut or something, sometimes they'll have you put hydrogen peroxide on. Hydrogen peroxide basically goes in to destroy the bacteria. So for those of you that are going into the nursing or medical field, that might be something that's, oh, you got something infected?
Nurse Connor.
Oh, Lord.
Well, I thought they're discouraging that now because it messes with the healing process.
Okay, but so you notice that hydrogen peroxide, H2O2, in an acidic environment, this is going to be important, in an acidic environment, is a very, very, very good oxidizing agent. Okay? So, and then you've got like, and here's the cool thing with this. So now you have the permanganate ion. Now, there's a couple of things that you have to be careful of. So, there's actually two permanganate ion reduction potentials. One is that you turn it into MnO2 plus water, and the other one is that you turn it into Mn2 plus. Unless I specifically tell you that you use MnO2, what we're going to do most often, what we're going to do is the one where it turns into Mn2 plus. That's the one that I will, unless I specifically tell you, oh, this just goes to MnO2, it's going to go all the way to Mn2 plus. Okay? So just be aware of that one. Now, the other thing to watch out for, and the other one we use a lot, is dichromate, okay? Because of the fact that that's a very, very good oxidizing agent in an acidic environment. So you notice that on almost all of these, whether it's a polyatomic ion, that these are all done in acidic environments, mainly because of the fact that they're going to have oxygen in these and you have to have the waters to balance these out. So here's how this might play out, okay? So let's say that I gave you a list like this and said, okay, you have silver ions, you have nitrate ions, and you have, I don't know, dichromate ions. Okay? So let's say that you've got these three. And I said, okay, silver ions, nitrate, and I want you to rank them in order of strength as an oxidizing agent. Okay? So what you list first would be the worst oxidizing agent, and what you list last would be the best oxidizing agent. Okay? Got that? Mm-hmm. So here's what you have available to you. You have silver ions, nitrate ions, and dichromate ions. So basically, when I ask you to rank them in order of increasing strength as oxidizing agents, what are you going to look for? Their ability to lose electrons or their ability to gain electrons? Their ability to gain electrons, right? Okay? And that's the game that you got to play. Oh, these are oxidizing agents. These are willing to gain electrons. So if you were to look at a reduction chart, would you look for these to go in the direction that it's written or in the reverse direction that they are written?
The direction that it's given.
Right? Because of the fact that you're looking for oxidizing agents, you're looking for ones that would be willing to take in electrons. So, mathematically, what are you going to look for?
Positive ions.
The highest positive or the lowest negative E naught value, right? So what's the E naught value for silver?
0.8.
8,
Well,
0.8.
0.80?
Yep.
Yeah.
depends.
Okay? Everybody cool with how we got that number?
Yeah.
Okay? Now, what about the nitrate?
0.96.
0.96. And then what's that dichromate one then?
1.33.
1.33. Okay? So, if you look at these numbers then, remember the bigger the positive value is, the more likely it wants to go in that direction. So of these, you got nitrate at 0.96, silver at 0.8, dichromate at 1.33. So which one of those three is going to be most likely to go in that direction?
Dichromate.
Dichromate. So you got to figure your last one on the list is going to be Cr2O7 2 minus. Okay, so that's going to be very, very likely to go in that direction. So that's going to be the last one. So what's going to be the first one?
The silver.
Now, here's one of the things that you have to pay attention. Are you talking about silver or are you talking about silver ions? Because they're completely different. Okay?
Silver.
Silver ions are going to be is a relatively good oxidizing agent because it's be willing to take in electrons. Elemental silver would suck at it because if you say, well, silver would be a good oxidizing agent. So what you're saying is that if silver by itself would be willing to take in an electron and turn into Ag1 minus. So if you tell me silver is a good oxidizing agent, you're telling me that this is what's going to happen. Now, in your esteemed chemistry careers, have you ever seen Ag1 minus?
Well, not like that. No.
No. You know why?
It's not esteemed enough.
Yeah, it doesn't exist. It's not stable, okay? You're not going to have silver gain an electron and turn into an anion. So Ag is not even in the realm of possibilities to act as an oxidizing agent. Now, silver ions, hey, that's all day long. We can talk about that. So silver ions are good oxidizing agents. Elemental silver sucks at it. Okay? And so that's what you have to keep track of. Are you talking about the element or are you talking about the ion? Because they're two completely different things. Okay? All right. So, now, the converse of this, I could give you something like this and said, okay, I'm going to give you iodine, I1 minus, solid silver, solid iron, and solid aluminum. And I'm going to ask you to rank these in order of okay? So, let's talk about this. So, you got iodide, not iodine, iodide, elemental iron, elemental aluminum. Okay, that's so. Okay? And I want you to rank these in order from weakest to strong, or strongest to weakest reducing agents. Okay, and that's the other thing when you get into ranking, you have to pay attention to how the ranking is asked to be done. Is it from strongest to weakest? Is it from weakest to strongest? Because they play out completely differently. So, if you're trying to find a reducing agent, what are you trying to find?
One on right,
The what?
the one on the bottom right, like with the lowest value.
Okay? Because are you trying to make these things gain electrons or lose electrons?
Lose.
That's right. So at the end of the day, I want the one that's ranked first that is most willing to lose electrons. Okay? Now, here's what you have to pay attention to. over here, because of the fact that, let's say for example, I'm starting over here with aluminum, okay? And when you talk about aluminum, the only place aluminum shows up is the product of a reduction equation, okay? What you don't see Al plus 3 electrons turning into Al3 minus, okay? You don't see that, okay? It's not there, because aluminum isn't going to gain 3 electrons and turn into Al3 minus. It's not going to happen, okay? Now, you can have aluminum ions gaining 3 electrons and turning into elemental aluminum. That can happen, okay? It's cool. So, but what you can do is you can take this reaction and you can reverse it and say, okay, hey, I can take aluminum. Is it willing to gain or lose electrons and turn into Al3 plus? That's fundamentally what we're trying to figure out. So again, let's play the numbers game. So if you look at this, right? So the other thing when you look at this, so you've got iodine, which is, where's iodine?
Is that the top-ish?
First column, bottom.
First column towards the bottom, right? So that's 0.54. And then you got iron.
Wouldn't it be negative?
Well, I know, but I'm just writing down the numbers that are on the chart.
Oh, okay.
But yeah, you're right. It is going to be a negative value because of the fact that basically you're going to take that and you're going to reverse this. So now with iron, here's what you have to be careful of with iron. Iron can be turned into Fe2 plus and iron can turn into Fe3 plus. What iron will, unless you're specifically told something different, always choose iron to be Fe2 plus. Okay? So Fe2 plus, the way it is written, is negative 0.44. So if this is going to happen, I'm going to reverse that sign, and that's going to be 0.44. And then the same thing with aluminum, which is
1.66.
1.66. Okay? So if this is the case, allowing for what I have, which one of these is going to be the strongest reducing agent?
The aluminum.
Aluminum, because that's going to be most likely to give up the electrons. Then what?
Then the iron.
And then the iron, and then the
Iodide.
iodide 1 minus. Okay? Does that now kind of begin to make sense? Okay.
I think so.
Now, here's the other way that this plays out. Okay? And we'll do the demo here in just a second. I don't know which one I've got set up. Okay, so here's how sometimes you see these questions played out, and it's like you kind of have to understand the code. So the question is copper capable of reducing silver plus? Now, what they don't tell you is the end game. So if silver is going to be, silver ions are going to be reduced. It can either turn into Ag2 plus, or it can turn into silver. So in this situation, if you're talking about copper capable of reducing Ag plus. So what we're saying basically are silver ions capable of taking electrons from the copper, and if that happens, are you going to turn it into elemental silver, or are you going to turn it into Ag2 plus?
AG.
Elemental, right?
Yeah.
Okay. So here's what we're going to do. So I'm going to take some copper. Okay? And I'm going to pour that into some silver nitrate. Okay. Nitrate. Drop that.
Oh, cool.
Oh, what it did.
It does make silver.
Okay. Okay. So we'll let that sit there. Okay. We'll let that run for a while. Now, the other thing I'm going to do is that I'm going to take a piece of copper, okay, and then I'm going to dump that into a solution of calcium nitrate. Okay, so that's copper in silver ions. This is going to be copper in calcium ions. Okay, so one is Cu, one is Ca.
Did you mean to pour both in there? Into this one?
Huh?
Did you mean to pour both into this one?
No, they're both. I just added to it
Oh,
so that it was completely covered up. That was all.
sorry,
Okay.
Anna. Oh, no.
That was
So-
great cinematography.
Let's play the numbers game on this one. Okay? Huh?
Do you still have that one?
Have what?
The ladder.
No, it's in the still in the teacher's lounge.
Okay, thanks.
I thought she said water. What water? Okay, so let's play the numbers game here. So basically what we're saying is if this is going to happen, Ag plus is going to gain an electron and turn into silver, right? And then what's the silver? Then what's the copper going to do?
It's gonna lose
Copper is going to turn into
copper 2 plus probably.
two electrons, right? Okay, so unless you're specifically told differently, you assume that copper is going to turn into copper 2 plus. So look at the E naught values, okay? So the way this is written, and here's what's important. I am starting off with silver ions. I am not starting off with silver atoms. I have a solution of silver ions. So what happened on an atomic level, here's this copper, okay, that solid copper, and it's going to be dropped into an ocean of silver ions. So the question is can that silver ion go up to the copper and go, hey, yo, give me your electrons? And is the copper willing to give up those electrons to end up at a lower energy state? Okay, that's the fundamental question, okay? Is this reaction spontaneous? That's the question. So if this is going to happen, so this one is going to go, it's kind of the biblical thing, as it is written. So what's the E naught value as it is written for silver gaining an electron and turning into Ag?
0.8.
0.80 volts, right? That's a positive value, which means it really wants to go in this direction, okay? Now, but what would we have to do with the copper?
Reverse.
Yeah, because again, we're not starting with copper ions. We're starting with copper. So the only way that can happen is if I have to find copper as a product on this chart and then reverse it into Cu2+, okay? That's the whole key to this, is that I've got to start with elemental copper and reverse that. So if you find that one, which is
Top of second column.
0.34, but then I'm going to reverse it so it's going to become
Negative.
negative 0.34. So if I take 0.8 and add that to a negative 0.34, do I get a positive E naught value?
Yeah.
Yes. So is the reaction going to happen? Yes. So that's why what's happening there is that on that copper, you formed all of this nice silver. So what's happening is that you are forming elemental silver. Now, so what's happening to the concentration of the silver ions in the solution? It's going down, but the concentration of the copper ions is going up. Okay? Brent?
Why can't we just use the yellow chart for those numbers?
You can, but what on the assignment today, you've got
Oh, okay.
ones that aren't on that chart that you need this one for.
Oh, okay.
Okay? That's why. You can use that, but this one is a much more comprehensive chart. Okay? Now, let's look at the other one. In the other one, I dumped in a strip of copper into calcium ions. Okay? So now, if you play the game the same way, is copper capable of reducing Ca2 plus?
Mm-mm.
Okay? Why not?
Because it's not spontaneous.
Why not?
Because like it would lead to a negative E0 value.
Because
Okay?
calcium ions turning into elemental calcium have a really high negative voltage.
Yeah, so if you look at what would happen, okay, and both of you are right. So if you combine both of these, you come down here and you find calcium, right? Calcium has a very, 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 very large negative E0 value. So does calcium want to exist as elemental calcium, or does it want to get reversed and turn into calcium ions?
It likes being an ion.
It wants to turn into calcium ions, okay? So right away, if you look at this, okay, that Ca2 plus, that's a large, large, large negative value. So that would have to stay in this direction, okay? And then you kind of up here and you find that copper. That really doesn't want to go in that opposite direction. So this is why, even though I put copper into two clear solutions, in one situation with the silver ions, it's going to plate it out. The other one, nothing's going to happen. So you can actually do that like sometimes on Christmas, you'll do that, teachers will do that, they'll make like a little Christmas tree of copper and they'll put it in a silver nitrate solution and it makes like little silver Christmas trees.
Wait,
He's so
didn't we
big.
do that in Chem Club? Pretty sure we did.
We had like ornament.
What is
Okay.
What is VO? What is VO?
Where?
On the reduction sheet? VO.
No, which column?
It's on the
First
first
one.
left column, about bottom of the mid.
Ion?
VO.
Oh. VO2. Yeah.
What is that?
Vanadium? Vanadium oxide?
Is that a thing?
Okay.
That is an element. I have tiny walnut brain.
So let's say I gave you this question. Are hydronium ions capable of oxidizing silver?
So if you pour in hydrochloric acid.
If I drop a piece of silver into a solution that contains hydronium ions, could be an acid, water even actually contains some.
No, because they have a 0 voltage, so it would just reduce it. Because
Can
I'm
zero be
done.
negative?
I'm done.
Like-
No, you're okay, Brent. You're okay.
No, like, so the hydrogen ions have like a voltage of 0, and if you added the silver, like solid silver, it has like a 0.8, so it would be a negative 0.8, so it would be reduced and not oxidized.
And
Okay.
it doesn't want to do that.
Maybe.
Yeah, it's fantastic, okay? So if you look at what's happening with the silver, right? So what would have to happen is that the silver would turn into Ag plus 1 electron. Now, what this would physically mean, okay, is that the silver would dissolve. That's the other way that this could be asked. If you dropped a piece of silver into a solution that had hydronium ions, would the silver dissolve? Okay? Now, we use silver in jewelry. Do you know why?
Because it doesn't do that.
It doesn't dissolve, right? Water contains hydronium ions. If the answer to this question was yes, okay, then you wouldn't want to wear silver in water because water contains a certain number of hydronium ions and it would dissolve within the water, okay? So if you look at the elements that we use in jewelry, okay, you got the big three, silver, gold, and copper. Notice that those are pretty high up on the reduction chart in their products, which means they really want to exist as those. You know, someone says, hey, I'm gonna buy you a potassium bracelet for your birthday.
Heck no.
Don't wear it, okay? Especially in the shower or whatever, because of the fact that that potassium wants to give up electrons and turn into potassium ions, okay? So, now,
But cadmium's also bad.
what if I said this? Is hydrogen capable
Yes.
of oxidizing
Yeah, yeah, I agree.
Yeah.
zinc?
Yes,
Yeah.
because zinc it would have a positive value.
Now, what I would recommend, this is a reaction that you've done in Chem 1. You took a piece of zinc, you dropped it in hydrochloric acid, it vigorously bubbled, very exothermic, you generate these hydrogen bubbles, you collect the hydrogen bubbles, and, you know, make the test tube bubble.
Roll around.
Classic.
And then
So, in this situation, if you're not sure, get a couple of reactions that you can use as a pattern, okay? Okay, hey, I know if I drop zinc into hydrochloric acid, I know there's going to be a reaction. Then use that as a trend on this chart, okay? If you like to play the over-under game, play the over-under game. If you like to look at the mathematical E0 values, look at those E0 values. I don't care, okay? But find some way of figuring this out. So the first one is no. The second one is yes, okay? So again, don't wear zinc. Now, but what if I gave you this question?
Yes.
Well, we can't deduce that.
You
But
deduce
from
the-
the second one you could, because you said what if, and indicating that.
What are you
Okay.
talking about?
Now, is hydrogen gas capable of reducing silver ions? Okay? So what you would physically do to make this happen is that you would have a solution of silver ions like this, and you would have a source that was generating hydrogen gas, and that hydrogen gas would bubble up through it. Okay? So if the answer to this question is yes, you would begin to see silver very slowly form in the test or in the beaker or whatever you're doing this in. Okay? If the answer is yes. If the answer is no, then nothing's going to change. Okay? So here's the million-dollar question. Is hydrogen capable of reducing silver ions?
No.
You sure?
Yeah.
Oh yeah, because this is reducing it.
Okay? So here's the deal.
It's so hard to keep track.
No. Okay? Now, what I didn't put on the end of this is reducing silver ions into
Solid silver.
elemental silver. So the way it is written on the chart, Ag plus gaining an electron turning into elemental silver, what's the value of that E0 value? What's that E0 value?
Point
Point
one.
A.
Positive 0.80, right? Now, what about the hydrogen gas? That's 0, right? So even if it gets reversed, guess what?
It's still zero.
It's still 0. So the answer to this question is yes, it will do it. So if you take, like that solution of silver nitrate, and you release hydrogen gas into it, it's going to bubble up. What you will see over the period of time is that you will see bits of silver begin to form within the solution. Okay, it isn't like, oh, we're gonna put in 1 drop of hydrogen and then it's all silver, okay?
That'd be
Right?
great.
It would be, don't get me wrong, okay? But that's not what's gonna happen. Okay, so you got the idea. Okay, so shut off the camera for a second.